Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Rocket Monday, we're going to talk about scramjet versus rocket engines. So let's dive right into it. Recently I've noticed a lot of hype around it. So what the heck is this scramjet? Well, it's just an air breathing engine. Basically rocket engine is an engine, but it does not require air. It's independently fulfilled, so to say. The oxygen requirement is provided by the propellant department. So this system is specific type of engines that are designed for high speed, meaning this is also an air breathing engine. It does work, it's awesome, but it does not work at very high speed, meaning this puppy will barely go to Mach 1.2, and the moment you start to go farther than that, this is like, I'm out. It will fundamentally not work. So if you need something that goes ludicrously fast, you go into what we call supersonic ramjet, because you have to understand inherently there's only two types of jet engines. One is normal jet engine, another is ramjet. Now what does ramjet means is simply because it's a ramming itself through the air. There is nothing that is sucking air in. You're just driving so fast that the cone that you have in front of it, that itself is providing the compression. So that's why we call the ramming effect. So you're just moving through and air itself is getting compressed through the cones that you have. Now, if this air compression that happens, you have to understand this. You cannot get anything for free. So if air is coming in, like say for example in Concorde, air is coming in Mach 2, super high speed, but very low pressure, because again, it's very high altitude. So what you do, you design a shock wave in such a way that air gets converted. Basically, you design shock waves as a what we call transformer. You transform the velocity into pressure. And benefit of that is that your engine now breathes in pure high pressure low velocity air, meaning the air that is going in the course of engines, that puppy is like subsonic. So engines are like, I got this, fam. So you take supersonic, you make it subsonic. That's how, basically that's how the conversion is happening. Basically you're taking high voltage and low amp, you're converting into high amp, low voltage. So that's how it works. Ramjets, that's what they do. But there is a subcategory of ramjets where the increased speed is so high, like let's say Mach 5 plus, or even at Mach 4, it starts to happen, that air, even though when it's slowing down, is still at supersonic. That's what we call supersonic ramjets are scramjets. So for example, if you're making a BrahMos missile, which is one of the fastest cruise missiles, so what they have is a solid booster. Now this puppy accelerates that, because be mindful, ramjet can only work if there is a ram effect. Ram effect requires speed. So slowest ramjet I know is can still starts off around 500 kmph, meaning if you are below that, that puppy will not start. You cannot start it out of a runway. So all the cruise missiles that are using ramjet or scramjet, generally all of them are ramjet only at this point in time. So they use solid boosters. That booster gives it at Mach 1 or Mach 2. So the ram effect starts to take over, and then the booster falls away, and jet engine is like, I got this. Jet engine, the ramjet turns on and it takes care of it. So if you have that system and air, even though after going through compression, shocks and all that jazz, it's never slowing down to subsonic, you call it basically scramjet. Now, you add fuel to that compressed air and voila, thrust. Basically exactly same thing what happens in normal jet, but you do not have any moving part. That's why this puppy can work at very high speed, because the drag of the engine is exponentially lower compared to anything that has moving parts inside. So like this, from a high speed air point of view, it's like this is a brick wall. This is just a hole. So this puppy can go at very high speed. There you go. High Mach speed cruise missiles. Like this puppy can easily cross 3.5 Mach. Basically, it's like what SS-71 does, but for cruise missiles, like much cheaper. So no moving part goes there. And if you can somehow go so fast that even after slowing down, basically even if you converted a lot of velocity into a lot of pressure, the velocity is still high, meaning your intake velocity is too high. That's why ramjets will start at around, let's say, 500 kmph. Scramjet does not even think about it unless you are already at like Mach 2.5 or sometimes even more than that. Generally, it says it's much better to try at Mach 4. So that's scramjet. So what are the problem? Why can't we just have this Maverick going Mach 10 and all that jazz? Well, we have the fuel for the job. That's one problem solved. Like, do we have a fuel? Let's say, do we have a hydrocarbon fuel that has enough oomph to get this job done? Yes. Then what's the problem? Well, problem is oxygen supply. How the heck are you going to combust that fuel? Why the heck our rockets go so fast? It has its own oxygen. It works. We can go at orbital speed, which is ludicrously fast. So why can't we have our jets going that fast? It's simply because air is not dense enough. It does not have enough oxygen in it. And there lies the paradox of making this sort of jet, be it SR-70 or be it SR-72, is that if you go in low altitude, basically 40,000 feet, let's just say, you have more oxygen. That's awesome. More fuel you can burn. But here's the drag goes up high, because again, the atmosphere is very thick. So the drag on you is brutal. So all the benefit of more oxygen is negated. But if you go up higher altitude, let's say rather than 40,000 feet, you go to, let's say 80,000 feet, then you reach a point where it's like, okay, you have high altitude, you have very low oxygen, but also you have very low drag. So you reach a point where it's like, it would be much better to pick up speed in vacuum, but then the problem would be where the hell you get the oxygen? Where will you get that air breathing part of it? So that's why. And all these engines, the moment they go into what we call a ramjet mode or scramjet mode, they cannot suck air in. At that speed, all you rely on is shock cones. You do not have any ability to suck air in, because from your vantage point, you are moving so far that air is bumping into you and you cannot suck more than that. And be mindful, everything around you is, if you are talking at like, let's say Mach 10, everything would be hot plasma around you. So you have to deal with that puppy also. So these are the inherent limitation, physics based. You cannot bypass it, you cannot trick it. You're like, what if I go much higher altitude? Yeah, awesome, no problem. Do we have fuel that can get the job done? Absolutely. Do we have oxygen? Yeah, no. At that altitude, let's say it is said that SR-71's top ceiling is 100,000 feet. Do I think that would be true? Yes, because again, its younger cousin actually did that. So it should be feasible. So that should not be. But can we go to 200,000 feet? No. At that point, oxygen is so low that unless somebody throw you from low altitude where it's like going super, super fast and then you just yoink to the street and like have a high going velocity, almost like how Jeff Bezos' rocket does that. Is like, shwee, you just throw it at high altitude, then you can do that, but you can't drive there. Like there is not enough oxygen. So that's the main issue. Air is the main problem. That air breathing part itself is the problem, because air creates what we call parasitic drag. These puppy engines are like, I'm awesome, I'm going to provide thrust. Where is the thrust going? You're just fighting the air. You're not moving, you're just fighting the air. So you have to push exponentially more power. So high speed and then creates another problem, because air is just not going to like move away. It creates that plasma cone that you see around it. That has exponential heating also, meaning at slow speed, your outside skin could actually get cold. That's why you have, commercial jets that have icing issue, like Iron Man 1 movie, icing issue. These puppies, like, it will dare ice to. It's like, come on, I dare you to form on my face. I dare you. This puppy is like, the hottest part can easily cross 300 degrees Celsius. The coolest part still would be 250 degrees Celsius. So this puppy can dare winter. It's like, I dare you to form ice on me. And at Mach 10, it will be like, I dare form anything around me. So this is one thing you have to understand. 316 degree had been achieved at Mach 3.2 of SR-71 skin. So the moment you go ludicrously high speed, the highest speed we have achieved is Apollo capsule. Second highest is space shuttle. Those puppy reached a skin temperature of 1477 degrees Celsius. Basically, at that point in time, there is no metal that can withstand its structural integrity unless it has actively cooling, for example, how rocket engine chamber survives, or it has to be ceramic. Fundamentally, nothing can take that much heat and be like, I got this. Structurally, it cannot. Like, it will look like a metal sheet, but it will be like plastic sheet. It will be like, it will become elastically deformed. That's why aluminum was not used. Even though you're like, hey, isn't 300 degrees Celsius low enough where aluminum can survive? Oh, absolutely. That's not an issue. It's just that it will not have the structural integrity needed. It will like, I'm aluminum, I'm strong, I'm not melting. Awesome. But here's the deal. You can literally at that temperature, of course, wear gloves, you can bend it like this. So that's why titanium had to be used. Nowadays, people are expecting some composite of ceramics and glass fiber that should allow to withstand this temperature for longer with minimal cooling or no cooling even. Or if you have enough ceramics, yeah, you can achieve this temperature and withstand it with structural integrity, or have ceramic outer side and metal inside. So how the heck you cool this puppy? Like, you can't run air condition at this. Well, the fuel itself was used, and the fuel was also another reason why this was so expensive, is that they required a special blend of fuel which was called, I forgot that, JP8 or 7, something like that. Basically, we use generally JP1 or some variants of that for normal systems, even for fighter jets. Then you have special mix that was built for this, so it does not self-ignite. This puppy gets almost 200 degrees Celsius. Flash point of most fuel is below that, so meaning your fuel will automatically combust. It will go boom. So for that reason, they had to have a fuel that had very low flashing, very high flashing point. So they required what Elon Musk uses to ignite his rocket engine, that green flash. This puppy had that to ignite the engines, electrical ignition system. Again, I think nowadays we can achieve high enough electrical oomph to do that. But back that time, they had like, okay, we're gonna give you a shot, and these shots will be 15 shots. You can start your engine. So fuel was used for cooling. So basically, they run the fuel through heat exchangers or around the body, and it's like once the fuel is like, I'm too hot, I'm already about to go boom. It's like, okay, go to engine and go boom. Now, if you start to achieve this sort of temperature, Mach 9 or Mach 10, you reach a point, you don't even need to go to Mach 9. I'm pretty sure this will start to happen at Mach 7, is that you will start to glow in infrared. Like so glow that is like, oh, hypersonic is invisible to radar. That is mathematically true, but it will glow like a star. Even in the most cloudiest, rainiest scenario, you can have a good infrared system. You'll be like, hey, I can see you. And you can see that like during Dragon capsule landing, many times there was cloudy environment and SpaceX switched to infrared feed, and you can see that. It's like you can't see that optically, but you can be like infrared, oh, that's what it is. So you glow in infrared, and as you increase speed, like Mach 15, yeah, you start to glow in visible spectrum. At that point in time, there is no stealth. You don't need radar. You're like, dude, that glowing thing. At that point, it's like meteorite. You will glow like a meteorite. And once you reach that critical point, you create a plasma wall. Once you have that plasma wall, radar cannot be reflected by it or penetrated, meaning you cannot have any communication, or you cannot like basically send any signal out, and you cannot receive any signal in. And that's why basically modern air defense systems, basically radar tracking systems that we use, they use very high frequency. They will simply just, they will fire the frequency, and frequency will just like lol, it will disappear out of it. That's why hypersonic cannot be targeted. If you are traveling at that speed where you have like, this sort of plasma wall around you, you are invisible to almost all radio waves. So fundamentally, and that's the odd part about this, is like they show the plasma wall, somebody studied that, but they're like full communication. I'm like, no. Like that's why if you watch any Apollo mission movies, you will see that when they are re-entering, where that plasma wall happens, there is radio silence. Same happens with space shuttle when it was going through, radio silence. Same happens with Dragon. You cannot communicate through it. And these three are very far apart, 60 years apart. So you can be damn sure that you cannot communicate. Is there any way to? Yes, if you use X-ray for communication. NASA did try to do that, X-ray communication, but right now it's not that mature where you can put that in a plane. But again, maybe military have that already, but other than X-ray, nothing can penetrate that. So if you have X-ray, then you can communicate to the outside and receive signal inside. So that's the part. And Ramjet or Scramjet does not start, because be mindful, Ram effect requires you to have air intake. Otherwise, it will simply not work. So Ram effect requires minimum 500 kmph minimum. So at best case scenario, you may able to fire a basically Ramjet cruise missile directly without having the solid booster. Maybe. That's a big ass maybe. Most of the time, they just design with the solid booster so they can land launch it, ship launch it, and air launch it is easier if you are not requiring to go very high speed. So there are some serious problems. That's why like these things were, even though it was made, it was like we were pushing it. Like could they made it faster? Most secret sources says that it was capable of going a little bit faster, not too much faster, because it's like, yeah, the outside temperature was like, bro, a fuel at that point in time is like, I can't cool more than this. Like fuel itself could ignite at that point in time. So what about efficiency? And you have to understand, anytime you're talking about anything, anywhere, you have to understand three layers of reality. First is physics. Does physics allow you to do this? Then we engineering. Can you actually do it? Third layer is economics. Can you afford to do it? So efficiency is critical aspect here, because jet engines are efficient. That's why we have jumbo jets. That's why we have the luxury of traveling from one place to another. We can literally have flight of 12 plus hour continuously without refueling. We're just like take off, 12 hour in the air and then land. By the way, we can even push that puppy to 24 hour or 22 hours. So we are damn efficient. Imagine it, like there is a thing, this metal tube that takes off a lot of people, like around 100 plus people, or maybe even 700 people, and then just like lol, stays in the air for hours without refueling. Hours. Not one day, not 2 days, but hours. So we are very efficient. How? This is what we call specific impulse on this axis. This is Mach speed. So specific impulse of rockets, you must be familiar with the fact that you will barely get 500. If you have ludicrously like a real world, 400, 450. So you are always below 500. Let's just put it that way. No matter which rocket system you use, you will always be below 400. Jumbo jet, let's say General Electric CF6 engines, these puppies that are on B747, Boeing 747, can give you around 6,000. That's high compared to rocket. Like a rocket can barely give you 500. That's why rocket burns out so quickly. While jet engines is like, I can keep on going. I can keep on going. Hour number 20, I can still keep on going. That's the reason, because of the efficiency. So, well, then how the heck we have this sort of efficiency? Because here's the deal. At subsonic speed, drag is surprisingly low. Yes, there is still drag. Yes, engineers will spend days, years of their life just to optimize the drag even bit better. But at slow speed, basically subsonic, everything is efficient. The moment you push beyond the sonic barrier, more speed equals exponential drag. So drag does not go high like this. It goes yol. It's exponential, meaning you're like, oh, Mach 2, let's say X amount of drag. Mach 3 will be like 50 times more than that. It's that brutal. So you cannot go there. And the reason rockets can go at orbital speed is basically that's the first thing they do. Bypass the atmosphere. Go through the atmosphere as quickly as possible. The moment you cross the atmosphere, become parallel to the orbital direction and then fire and go. And you go fast, as in like Mach 25 kind of fast. That's why rocket can do that, because it's accelerating in vacuum and it has its own oxygen. It does not have to suffer the consequences of air breathing. So best rocket can give you 500. And here's the scramjet, many times people who do not understand it thoroughly, they describe that you have the efficiency of a jet engine and speed of a rocket engine. Technically not true, because here's still the moment you increase the speed, the efficiency goes down. This is physics based, you cannot bypass it. So once you are talking about, let's say, Concorde engines, they will give you around 3000, less than 3000, still more than awesome compared to any rocket engine. Then you come to basically SR-71 engines that are patterned with these J48, 48 times like 58s, those were like around 1800. And you can notice that we came down from 6000 to around 1800. How the hell that happened? Speed went up. So you start to go into scramjet territory. Yeah, your efficiency is at this point in time almost similar to basically a rocket. At that point in time, you may be talking at most optimistic scenario 1500 specific impulse. Now you may be like, isn't that 3 times better? Not that much, because you have atmospheric drag. The moment you put that into compensation, it's like, yeah, it's useless. If you are getting this sort of mileage at that speed, then it makes sense. Then you can fight the atmospheric drag. But at this low efficiency, you're like, drag is so high that it's like, bro, I cannot do that. And you can see that even in SR-71, when SR-71 took off, it simply could not took off with full fuel load. It's like, bro, I just do not have enough efficiency to take off. It will like very minimal fuel, of course, with emergency landing in mind, and then it go to the basically air tanker, then fuel it up, then go at Mach 3.2. If it tried to do that with full fuel load, it will simply fail to take off from the runway. So you have to understand, drag from the air becomes brutal at higher speed and you start to glow like a star. This is another thing. This is one thing they got right in basically Maverick, is that the main ground-based camera, they were infrared. And trust me when I tell you, it will look through any atmosphere, like whatever is happening, be it fog, be it rain, be it whatever. Infrared, you will be like, ah, I can see you. It's the best way of tracking at super high speed things. So hydrogen is the best fuel to use for this, but problem is carrying capacity of hydrogen is 0, meaning how much hydrogen you can carry in 1 liter of volume is 0. What if you make it liquid hydrogen? A little bit, still would be less than 1 kilogram. That's why we do not use hydrogen for main fuel. It's stupid. And what if you use metallic hydrogen? The metal itself would be heavy. That's why we don't use it. And what if compressed hydrogen? Compare that kilojoule, basically megajoule per kilogram, you will be shocked how little it has. Like people say is like hydrogen and 150 megajoule per kilogram. That's awesome. Yes, deal. How much area did you took to fit that? Now you come to real world units, that is like megajoule per liter. Let's say a diesel gives you around 40 megajoules or even 35. Compare that to hydrogen, 1 liter, even liquid form, which is cryogenic. Yeah, nothing. It's that little. It's like 1/4 of the what you're gonna get. That's why this sort of theoretical maximum line of 143 megajoule per kilogram does not matter. It's like kilogram is not how we measure things. We measure in liters. Can you fit it? It's like, yeah, this 1 kilogram, but it takes like a 100-meter basically ball volume sphere to have that. What's the point? The drag itself will compensate for that. So generally people use hydrocarbon. So you may hear people talking about like we are planning to use LNG, basically natural gas, CH4. That's the best compromise that we can have between hydrogen and the ability to actually carry the damn thing. So, and given the fact that it's also cryogenic, it does have the ability to act as a coolant for a bit longer. So that's what we can do. And body to fuel ratio becomes brutal the moment you go like this. You're like, hey, I want to go faster. This is one thing that you have to understand. SR-71, while it did work, that puppy was 60% fuel by body weight, meaning what is this 100 ton? Yeah, it's a 60 ton of fuel. That's the problem. And you compare that to rocket is 95% fuel. The moment you start to go, instead of, let's say, what if I want to go Mach 4 or Mach 5 or like in the movies Mach 10, how small the craft was, I'm reasonably sure that will only work for a few seconds. The moment it goes to that Mach 10, fuel is like, bye, I'm gone. Rocket needs minutes of fuel reserve, and then only it can only work for 8 or 10. So even extrapolating based on that, assuming somehow you have very good engine and very good drag coefficient, barely 15 minutes, like not hours, like you're gonna get 15-20 minutes. That's another aspect you have to understand. That's why, and this ratio will change no matter what you do, no matter which magical hulu you do. You go high in Mach speed, your fuel to body ratio changes. This was another reason why the heck, like, SR-71 did not have bomb bays. It does not have a space for it. Fundamentally, it did not have space for it. They can make it better. Can they make a different SR-72 that has a bit higher speed? Yeah. Will it has capacity? No. Why? Fuel. If it goes faster than that, fundamentally it will consume more fuel. You cannot do anything about it, and its ratio will shift even worse. Now, again, if it removes, let's say, cockpit and simplifies everything, aerodynamic efficiency may go up a bit. Does not require subsystems of basically cooling a human, but I'm pretty sure computers also require cooling. So I don't see how that would be that much beneficial. You will be back to a point where it's like, yeah, it really cannot fly for very long. So all you have to do is like keep refueling it mid-air. So that's the efficiency part. This cannot be bypassed. Then we compare this puppy to rocket, and rockets are complex, looks complex, but they are design-wise, they are dumb simple, meaning they are so simple that we achieved this puppy in 1970s, as in like 1969. And that's the reason why rockets always have this sort of curve. The reason is they try to go up as quickly as possible. The moment they clear the atmosphere, they're like, lol, peace, I'm out. So that's how they achieve speed, because they're achieving speed in vacuum. There is nothing fighting against it. So they really let their wings out, and they can go very, very stupendously fast. And what kind of speed we are talking about? Well, common people are not aware of like what is orbital speed. It's speed god, meaning you're talking about Mach 25. By the way, it goes even further than that. For example, this is a footage from real world Falcon 9. That puppy is at 35,000 km per hour. Let that sink in. That puppy is fast. 35,000 km per hour. And ICBMs at this point in time is the fastest thing. Like, we genuinely kind of forget like how god tier weapon ICBMs are. I'm not talking about the new part on it. I'm talking just the delivery device. Is that there was a joke written on Minuteman launch bunkers where it was like 29-minute delivery all around the world, or the next one would be free. And they were not joking about that part. It can actually touch any location on the planet in 29 minutes. Let that sink in. That's how fast it was. We kind of forget like how scary that was. Like, somebody could do something and 30 minutes later the disaster would strike. Wherever you are on the planet, does not matter. Wherever you are on the planet, wow. And why the heck these things are that fast? Well, they do not have to worry about max Q. They are designed, again, they are military equipment, so they are designed a bit more robust. It is not like, oh, I'm like, bare minimum cost competitive. No, like robust. So they push through max Q. They're like, oh, max Q. They push through it. Another aspect, there is no human tolerance or weak fragile electronics tolerance. So they design it to go as fast, as hard as possible. Because if you take Saturn V and you remove all its control equipments, where it's like go YOLO, it will catch up very high acceleration speed, because when it starts, it's too heavy. It's like, I'm barely holding on, barely going up, but once it starts to go up, the fuel load starts to go down, speed starts to build up. It's like, I'm good. Slowly it reaches a point. And at that point in time, it has very little fuel left, only let's say 1 minute of fuel burn left, but it's light. And the engines are still producing same amount of thrust. If it does not have throttle control, it could literally reach 8 Gs or even 9 Gs. Basically, it will look like a TV show Expanse. Basically, that amount of acceleration will happen. ICBMs, that's why they are so fast. They do not have throttle back, where they're like, no, bro, we go hard. We go as hard as possible. Hardest I have ever even came across was 100 G of acceleration going upwards. That's stupid fast. That's why whenever people do things like hypersonic is the next thing. Did you forget that we had ICBMs for like, 60 years? That's fastest. That's speed god. Like, that reached a point where it's like, it's like, what are you trying to, like, and this, to give you another context of it, ICBMs, you will always talk about people, like, you have to hit ICBM. Like, if ICBM in space, you have to actually hit it. Now, I always find that odd. It's like in air, when we do countermeasures, we have things going boom next to it. Now, here's the deal. If you try to go boom next to it, it is so fast that, let's say you are going there, radar waves going ting, coming back, detecting, it will be now almost here. It goes boom, the shock wave will take time. Like, shock wave have physical time. Assuming your trigger happens instantaneously, it still has physical lag, like how long it will take to reach the shock wave. This part, it's like, I'm out. That's why you have to actually hit it. There is no other way. Or you wait it to reach in atmosphere. Now it starts, atmosphere starts to slow it down. It glows like a, star. Use infrared tracking, then hit it from bottom. But it's too close and there is a very good risk it may have air burst. If it has air burst, it's already too late. But that was the idea. It's like if somebody designed something that goes very close to the ground, goes maximum devastation will happen like, around 1000 feet above the ground, that kind of place, you can counteract it before that. But generally the problem is, once it's in atmosphere, there is a very high risk. It's already designed to go boom. Like it already is starting to count down. You do not have time. Even though you can intercept it, it's just like, it may be too late. Again, if somebody had fired you, of course you will fire everything. But the ideal position is in space, but consequence is tiny thing traveling at idiotically high speed, God speed, and you have to hit it with another God speed. Otherwise, like nothing, no shockwave can travel fast enough to counteract it, unless it's another nuke, which be mindful they tried, and the results were not encouraging. So we come down to the final layer, that is economics. You have to understand physics, engineering, economics. So economics, you have to understand, it matters, basically cost matters the most in everything, be it war, be it peacetime. It's the one thing that matters. And if you can't afford it, you can't have it. You're like, we built SR-71. It's like, how much did it cost you? Yeah, too much? Put it in museum. You have to understand, like B2 is amazing. How much did it cost you? Too much? Put it in a museum. That's the whole thing. And hypersonic jet, let's compare it. A hypersonic jet will cost exponentially more than X-37. It's a real thing, has been launched, it's in space, and it's running at God speed, orbital speed. So that creates a scenario where it's like, this puppy can stay in space for years. Meaning, if done correctly, if a flotilla of those things are launched, basically let's say 10 or 20 of them, you can have them going through places that you think would be like, I think this place is steering some trouble. You can have them go crossing that orbit, and you will be like, I can have a look at you whenever I want. There's a thing that is coming there. And if some other place that is like not covered by your orbital plane, orbital planes can be changed. Of course, not very quickly, but it can be changed. And if you have enough of them, there will be one that is like only few hours before this puppy starts to go over it. And then because it has bomb bays, basically it can open it and just observe thoroughly. It can even fire. Again, they don't need to or desire to. So they're like, we got you. Now compare that sort of surveillance ability versus SR-71s, or even let's say Maverick's Dark Star. This is like, bro, I'm always there. Like, be mindful, 900 days achieved, past tense. Like you build a hypersonic jet, this will look free comparatively. That's how expensive that would be. So that's the reality. And you have to understand, a war, no matter which sort of system you are, no matter what you do, war is always about logistic and money. If you balance these two out, you can survive. If you don't, you're dead. And scramjets, many times people talk about, how about we use scramjet to boost rockets? Yeah, that's dumb. Super dumb. Why? Because scramjet only comes into effect very weird position where it comes, basically the ideal situation, let's say you want to put it in Falcon 9, it will be literally in between when stage 1 is completely spent, but let's say it's giving last 20% of its oomph, last 20% of its burn time, and before like first 10 to 20% of the burn time of second stage. It has to be in between stage. What's the point? And it's directly going up, so its thrust output will not be stable. It's directly going up because again, rocket has its own oxygen supply. Scramjet will require a perfect orbital system. Basically, not even orbital. It has to be like, I'm traveling parallel to the ground. Yeah, it makes sense. But other than that, it does not. And not to mention the specific impulse with that kind of complexity, that 100 ISP is not worth it. If it was like 6000, yeah, it would be worth it. At 1500, it's not worth it. So scramjet is simply useless for rocket. Why? It adds extra cost and extra complexity. And engineering hates that. Engineering is very simple. Kiss it. What is? Keep it simple, silly. If you don't kiss it, it goes boom. You have to kiss it. So that's why economics never suggested this sort of system. And that's why once military built this, tried to run it, and they were like, nah, this is not gonna work properly. They're like, yeah, let's just build flotilla of X-37s. It's much cheaper, much more effective. Even India is doing this. So reality, these things are far more dangerous than these puppies. They look impressive. They are amazing piece of engineering. Not really that useful. So this was my presentation on basically hypersonic hululu that is going on, basically scramjet technologies. Hopefully you have liked it, learn from it. In that case, please click the like button, share it amongst a friend. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.